the time that I will be very efficient here. Okay, so I look at here, the tin is get oxidized and then Ag get reduced. Actually, this is a perfect question for us to understand the what is an N here. Okay, so if you look at that tin should be oxidized, right? So I'm going to write tin is going to so I think that I will stick to my old-fashioned way. So tin, if you look at the table, this will be the way that is written. Okay, so always written in the reduction potential, and the E naught reduction is minus 0.14 volts. And I look at the table, and then I also find out Ag plus, so electron is reduced, and there's an Ag naught, and that's the one 0.80 volts. And then which one is a winner? This is a winner, right? This is a bigger value in this full chain, that which one will get the reduction. So now I know this will be written in this way, and as a consequence, this will be the one should happen the other way, because this value is smaller than 0.80. Okay, so this should be now changed into an oxidation. This will be a reduction as it is. So because of the way it is written now, I spent the time to understand it. So I am going to rewrite it. Okay, so I guess this is a winner, so there will be the one, but I have to rewrite it. This is a new form saying that, okay, tin will be lost, and then tin 2 plus will be generated. These are 2 electrons will be made. Okay, so these are the equation that I shown up here are essentially the half reactions, and these half reactions now has to be completed, and this one is not simple because one reaction, the tin reaction, 2 electrons are being generated. This one is a 1 electron. So you need to do here is, okay, I'm going to multiply this by 2. Okay, because essentially these electrons has to be going away. So I just multiply everything by 2 on this side. So it's make it easier. So I just multiply everything by 2, and then if you add them together, the net reaction, this is gone, but that means that N is 2 here. Okay, 2 electrons are exchanged in this reaction, and when you write the equation here, 2 Ag plus with a tin, and then 2 Ag metal with tin 2 plus. So that's cool. Okay, so that I can find out, and then they give me the concentration of tin and then ions and silver ions. So the way that is written, the Q value here is Ag plus, because it is a 2, so it's a square, and then that's the one is Sn 2 plus. Okay, so I only count this something that is a soluble here, right? This soluble here, and that's only being counted in here, and then I'm not counting this one for my Q calculation, right? Because of the Q, well, this is a very bright, the screen is very bright, so you guys cannot see that clearly. Let me see if I can change some angle to see if you guys can see that. Or this screen is probably very bright. Let me see. So it's so bright that I think that they are. Oh, you guys can see this one better. Excellent. Okay. Sorry about this. It looks better then. All right. Okay. So so that now you guys can see that as far as concerned, I'm just can use this one to calculate my Q, and then because of the way the reaction is written, then I can start to plug in the numbers. So my Q value here is what's my Ag plus is 2.7 to the square, and 0.022. Okay, and then what am I do? You're going to look at your reference sheet. You don't have to remember this equation. You just go and look at the reference sheet and then find out these values, right? So these values here, E cell is E cell naught minus NF RT over NF natural log Q. So that's the Nernst equation that allow me to calculate those numbers. And then what's my E cell here? E cell naught here will be this one. The reduction, keep it as it is. And oxidation, you're going to change the sign. So therefore 0.14 plus sign. Okay, so therefore 0.94 volts. That is you're going to be the value of your E cell naught. Okay, and then you're going to put everything there. So E cell, so let me show you one more time. 9.4 minus 8.314 298. I think, oh, okay, oh my God. Okay, so I'm going to put this one down here. Okay, so 94, and then N is 2, because of the N is 2, as shown up here. And then I am going to give you F is a 96500. Okay, that's a Faraday constant, and natural log 0.022, 2.7 to the square. Okay, and if you tally up, and then you will get the number that is going to be this number. Okay, I punch the numbers and I confirm that this number is correct. Although we are in a very hasty time, I wanted to mention to you about something that I repeated saying before. You look at this equation, right? And although I multiply this reaction by 2, I didn't multiply this voltage by 2. I just use the value as it is. And the reason is because, have you heard about intensive property? And have you heard about intensive property? No. Okay. Have you heard about extensive property? So some of them have done it, some of them have not. So extensive property is depending on the amount that you have. Okay? And intensive property does not change if you increase the size of the system. So, for example, let's say the volume, right? Volume is an actually extensive property, because if you increase the volume from this small to this big, small, and big, that's an extensive property. But temperature itself, if you increase the size of this small size to the bigger block, the temperature remains the same. And the thing that I explained it in the other cases, and you can do a little bit more study and make sure that E naught, okay, reduction, is an intensive property. Okay, so it doesn't matter whether you multiply this one or not, this value remains as it is. It is a good news for you, because it doesn't matter how this one gets multiplied by different numbers. All you gotta do is figure out which one do I keep it, which one is a winner, and which one is a loser, so that I have to flip this sign around so that I can use this E cell naught, regardless of how I multiply this equation to balance those electron numbers in and out. Okay, so therefore, this is something that I want you to keep that in mind. If you can study for it, it will be nice. If you have a question, you can. Okay, so is the oxidation value always going to have a negative E naught? The answer is no, right? Oxidation value always going to lose an electron. Okay, so let me show you this way. Oh, okay. I don't have a table with me, so let me go to my crash course and showing this value. Okay, so if I choose this one, right? oxidation. So this one, right? This one is going to the oxidation. So the E reduction potential is a negative value. In that case, oxidation is an opposite sign of that. So this will be positive. Okay, so that's the one. I think that when the student asks, is an oxidation value always going to have a negative E naught values? It is, if you think about it, if I have this one versus this, right? This one will be a reduction. If you think about it, this one is a bigger, this is a winner, right? And this scale, although they are all like to be oxidized, they are going to be pretty weak content in here, but this is a really weak, and this is a strong. So, you know, if I just compare this sodium and zinc is a winner. So what that means is they're going to go the way it is written. They are the winner. And then they're going to reverse the weaker side to going to the other way, right? So in that case, my value for this is minus 0.76 plus 2.71. Does that make sense to you, right? So it's an oxidation value is always a relative one, and then you will see the value that is spontaneous when you see that when you actually the E cell potential is a positive value, and then that's an answer. You guys can look at my other types of the solutions in the posting of the YouTube. Probably so. What will be E naught for AG and the CU? Okay, so I don't mind to solving this, and then maybe I can post this more answers to the later. So I'm going to go back, and there's a question about what will be the E naught. Okay, oh my God. Okay, what will be the E naught for AG and the CU? Okay, so in this case, so let's do this. Okay, so AG is a winner, right? So I am going to write reduction. So AG plus AG plus and the electron will be written in a way as it is. This computer is doing something funny. Okay, so AG naught. So they are the one winner, right? In this competition, this is a winner and this is a loser, right? So therefore, I'm going to rewrite this equation in the flip the other way. Copper will be losing 2 electrons and into copper 2 plus, making it 2 electrons. So those are the two half reactions, and because of that, the reduction potential is same, so 0.80. And then this one, E naught for oxidation, will be an opposite value of that. So minus, right? Because it's an oxidation, 0.34. And then my E cell is 0.8 plus minus 0.34, right? So you just add it up, and then you will have 0.46 volt. Okay, so that's what happened when you are using the AGs and one, because and I just focus on the answering your question, E naught, but to kind of elaborate here a little bit, okay, I want a net reaction. So this one is 2 electrons, so I just need to multiply by these 2. So to make it this one 2, to make it this one 2. But, you know, remember, although I have multiplied everything by 2 to make sure the electron can be going away, I don't have to worry about changing this. Once again, E naught is, okay, well, E naught, okay. I think that this one is E naught. They have some kind of funny communication here. Okay, so E naught is a intensive property, right? So therefore, I don't have to worry about those notations, the changes. And then when I add them together, your net reaction will be 2Ag plus, and the copper will be copper 2 plus and 2Ag metal. and then n here, in this case, is 2. Okay, so if you want to use a Nernst equation. Is that cool? Is that good? Okay. Okay, I love when students ask the questions. I don't mind to spending extra time, and so finish the rest of the problem. So let's see how far you can go. I have a couple of more, about 10 more minutes. I hope I can solve this one. Okay, so now the number 6, which battery is not based on the redox reaction? This one you have to look at the lecture slide by Kathleen. She mentioned about actually there's a slide about lithium-ion battery is not based on the redox reaction, and essentially it is based on the actually motions of lithium-ion. Okay. And you can find the lecture slide, and lithium-ion battery is not redox system. Okay, so redox means something got reduced, something got oxidized, and that's the way that most of batteries are working this way. You know, lead acid is in your car batteries. Okay, car batteries. Well, I think that they start to car batteries. And lithium, these are all the different one exchanges, the voltages in and out. Okay, so this one, the third one is quite a standard problem. So I wanted to see how they're going to sell. Okay, the cell potential here is they give me the cell potential, and what will be the concentration of H plus, right? And then actually they even give it to me the nice enough to say E naught is 0.76. So I think that I'm in a good business to know that. And if you start to look at that, and I mean you can do the right in the half reaction, but I can kind of see that zinc is zinc 2 plus. So there are 2 electrons involved. So N is 2 here. Okay. So this problem is a little bit more challenging because it not only deal with, so I'm going to ignore something that is a solid, right? But anything that aqueous, gases, you have to take it into account for what is called the Q, okay? And this is something that we have to take it into account. So in this case is Q, which is a quotient, is H plus 2 the square, and the zinc 2 plus. Anything that is in the solution that is shown up here as this value of the molar concentration. But as far as the gas is concerned, you have to use a partial pressure of the gas in an ATM unit. Okay, so that's the quotient looks like it. And then if you look at that, partial pressure is a 1 atmosphere pressure, so this is actually 1. And the zinc 2 plus, this is actually 1.0 molar. I think the problem was simple, much simpler now. So now this becomes H plus square concentration. That becomes our Q value here. Okay, so that's one thing that I know. And then E cell is E cell naught minus NFRT lnq. And what's my E cell? That's a cell potential is 0.53 volts. What's my this value, which is 0.76. This is a standard. Standard E naught, right? Is 0.76. So now I'm going to finish that up by saying, okay, the 2 electrons involved, 96500, 8.314, 298, ln 1 over H plus square. Okay, so I got all the numbers that you're shown up here. So then I can calculate, and so if you get this one, actually you will see that 17.9 is 17.9 is ln ln 1 over h plus square. Okay, so therefore you will get that h plus square is exponential to the minus 17.9. Actually, I can delete that, and I can make this one to. Yeah, I mean, you can work it out, and you can, if you just plug in these numbers to the h plus is actually e to the 17.7 to the half, and then you'll get the numbers that shown up here as a c. Okay, so that's the number that you will see. Okay, so I have a few more minutes, hopefully. Okay, so the electrolysis. Electrolysis is an opposite of the photovoltaic, or the voltaic cell. So electrolysis is more like you apply the electrical potential and you drive the reaction. And then magnesium chloride using the platinum electrode, right? Okay, so magnesium chloride means an Mg 2 plus and 2 chlorine minus, right? And then the platinum inert electrode. And so therefore, you can see that which one will be happening. Well, this one will be reduced. And then this one will be essentially losing electrons and to form the chlorine gas. So that will be magnesium metals and chlorine gas. So C is the answer for this particular questions. Actually, believe it or not, I think I can finish this one to my targeted one. So let me continue to do this electroplating. This one is actually quite similar to the electroplating question from the last year too. So they are asking this aluminum metal, right? And then, so you want to produce 4 grams of aluminum metal, and okay, aluminum metal atomic mass is 27 gram per mole. Okay, you can look up the periodic tables, right? And then if you look at where's aluminum, that's an aluminum, and if you look at the numbers, that's a 27, and that's the numbers. So then what I can do is grams of aluminum is something that I know what's the value, right? So grams of aluminum is related to the charges, which is a Q, which is a charges in Coulomb. And if you now if you know the charges of Coulomb, and this is 96500 Coulomb, is 1 mole of electrons, right? You know this, the unit conversion ratio. And so let me stop a little bit here and then talk about Coulomb. And the Coulomb is shown up here. Okay, so this is a molten AlCl3, so Al3 plus, right? And with an electrical current. So Al3 plus will be reduced by unit of 3 electrons to make 1 Al. So it's a 3-to-1 ratio that is going to be important here. And also the current is a 15.0 ampere. And this current equation is actually you don't have to remember. This is a Q. I wrote a capital Q, but it's the same. Current is an I and multiplied by T. So the ampere itself, which is a current, is actually Coulomb divided by second. Okay, so that's a current. This is a relationship that I can see. So what I see here is if I use the time in how many seconds, which is a t seconds, and that will be 15 times 0 times t. Okay, so let me just make a shortcut here. So that is will be this term. Okay, I just made a Q, but you can put in an equation later like that. And then the mole, so what do I do? Okay, mole of electron, mole of aluminum, right? That's something that you guys learn in the unit conversion. And what's the ratio? 3 moles and 1 moles. So 1 moles of electrons, 3 moles of aluminum. There you go. So and the moles of aluminum and the grams of aluminum. And where do I find it? Right here, right? So 1 mole will weigh 27 grams. So by doing so, I kind of, starting from the Coulomb taking care of, now generate how many moles of electron using the Faraday constant, and then moles of electrons are going away, and you generate moles of aluminum goes away, and the grams of aluminum. And that's the one that we wanted in the first place. So I'm going to tally up everything that I hear. So 4 grams is needed. So this equation now is 4.00 gram is 15 ampere times T, and 1 over 96500, and then 3 over 1, and then 27 divided by 1. Okay, so then all I need to do is solve it for the T, right? So that's a simple equation for you to, oh, what happened to this, my 27 here? 27. That looks quite okay. So you just realize, based on your understanding that you have here, it takes 3 electrons to produce 1 aluminum. So that's based on this chemical knowledge, I can establish this conversion from electrons to aluminum, and then I can do the electroplating problem, solve it this way. And the answer is D here. Okay, so I get a little bit went over time, and why the answers are red. I also, the why answers are red is because I downloaded the answers. I asked for the Kathleen to give me the one with the answer key. So I actually solved this problem in advance, and to make sure that my calculation is correct. So that's why. This is the exam with an answer key there. But if you go to the LMS, you can download the one without color coded, so the answer is not showing there. So you can do the practice for yourself as well. So it's just for me to ensure that my calculation was correct for solving this. Okay. Okay, you guys stay up quite late. Thanks for joining. And we have 13 students to join it, and I'm happy to see you at this late time. And I hope you guys have a